Computational materials modeling. We essentially were looking at plane groups, where we talked about generating two-dimensional crystals using simple MATLAB programs. The important thing for us to remember is a proper choice of the basis vectors, especially when it has the threefold symmetry. It's a good idea to actually choose lattice vectors which have a 120-degree angle between them, whether you have the six-fold symmetry here or the threefold symmetry here. It works well for both. Okay. We saw the following problem in last class, where we wanted to generate a plane group with P3M1 as its space group. We clearly saw that if you chose these set of lattice vectors, you are able to generate the crystal or the two-dimensional lattice in such a way that it has the threefold symmetry, and we demonstrated that that would not be the case if you chose a lattice vector that had 60-degree between them. So there is this needs to be kept in mind. So whenever you are generating space lattices also, a similar rule will apply. So you have to be careful in the lattice vectors that you actually choose in order to generate the space lattice or plane lattice. So with that being said, it's important for us to now move on and start talking about space lattices. So we talked about plane groups when we are talking about two-dimensional stuff. So when we talk about points arranged in three-dimensional space, we start talking about space lattices, space groups, and point groups in 3 dimensions. So naturally, once you are in the third dimensions, you have more possibilities. For example, you can have mirror. In this case, you had in the plane lattice, you had probably mirror planes which were having either the y-axis or the x-axis normal, right? Now once you are talking about 3 dimensions, you can have mirror planes which are actually having normal as the z-axis also, right? So in this manner, you can have rotations about one of the 3 axes instead of just the 2 axes, and so on and so forth. And you can have glide planes on all the 3 with the normals perpendicular with normals as either of the 3 axes, and we will have one more additional translational operator which we will see in a little bit. But the presence of these additional opportunities for you to create new symmetries within the structure gives rise to more number of point groups. So there are 32 point groups. How many were there in plane lattice? How many point groups were there? 10 point groups. And if you look at space lattice, there were 17. Okay. Now when you talk about when you talk about the space, 3-dimensional space, the total number of point groups increases to 32. There are 32 different possibilities, and there are 230 different space groups only. Okay, there are only 230 different ways you can basically arrange things in 3D, so that you have lattice translation, so that it is a 3-dimensional crystal, okay, infinite crystal. Just like how we looked at plane lattices, it's a good idea to actually study first the symmetry associated with the Bravais lattice. So what's a Bravais lattice? The Bravais lattice is only an arrangement of imaginary points in 3-dimensional space, such that when you sit on any point, it looks exactly the same. And there were 14 such possibilities when you talked about the space Bravais lattice, and 5 such things were existing for the 2-dimensional case, right? So some of these rules needs to be remembered when you are actually looking at the symmetry associated with the plane with the space lattice. The presence of rotation axis, 2 of these things, any 2 of the following symmetry elements will automatically imply the third. For example, a rotation axis of even order, a mirror plane normal to it, and an inversion center at the point of intersection of the axis and the mirror plane. The presence of any two of these things will automatically mean the other one. So if there is a rotation axis of order 4 and a mirror plane is normal to it, it means there is going to be an inversion center at the point of intersection of the axis and the mirror plane. You can just think about it. We already saw this example when we were discussing the various symmetry elements, right? The second one is the presence of any two mutually perpendicular mirror planes automatically implies the presence of a two-fold axis, right? If you have two mirror planes perpendicular to each other, then it automatically means that there is a two-fold rotation axis that is passing through the intersection of these two mirrors. There is no need for us to specify all the three things if they exist. The presence of any two will automatically imply the third. So sometimes you will find that one of the things is missing, what you think is obvious is missing in the Hermann-Martian symbol, but that is mostly because there is something else in some other symmetry operator that is present which is implying whatever is not there. Okay. So we will look at the symmetry of the Bravais lattices. The first Bravais lattice is basically the triclinic unit cell. So the triclinic unit cell means alpha and beta and gamma are all not equal to each other, and A is not equal to B is not equal to C, are basically characterizing the triclinic unit cell. So if there is a three-dimensional sphere at each of the four corners of the unit cell, then the only symmetry element that is actually present here is the inversion center that is located right at the center of the unit cell. Okay, that is the inversion center right there, provided whatever is there in the corners is actually an atom with spherical symmetry. So it might be a good idea for us to take a look at this picture. So at this point, at all these points you can see only spheres. At all the points you can see only spheres. The second I put some motive at that particular location, depending on what the symmetry of that particular motive is, you may or may not have this one bar. For example, if I put an arbitrary flower at that particular location, something like this, always oriented in that manner, right? Then this crystal is not having this as a symmetry. There is no one bar. The one bar instantaneously disappears, right? The only symmetry now for this entire space would be 1, correct? There is no other symmetry operator that is present. What we are talking about is for the Bravais lattice, which only has the atom there. This distinction is kind of important. It can be confusing at times. Next we talk about monoclinic lattices. So monoclinic lattices was like our oblique plane lattices, except that what is happening is you have a plane oblique lattice. Okay, this is A and this is probably B and this is some angle alpha, so this should be actually angle gamma. Okay, and you are stacking one more of this plane oblique lattice right on top of it. Okay, so that will give you this unit cell, and so it's characterized by beta is equal to gamma is equal to alpha is equal to 90 degrees, but gamma is not equal to 90 degrees, and none of the sides are actually equal in this case. So what are the various symmetry elements that is associated with this Bravais lattice? Okay, so it should be obvious that what's this? What are the various symmetry elements that you can think of? I'll mark this as A and I'll mark this as C. Okay. there is two-fold symmetry is there. Okay, on top of this I have stacked another one. There is only one two-fold symmetry about this B axis, right? There is a two-fold symmetry about this B axis. I am intentionally writing down the vectors as A, C and B. Usually the B axis is chosen as the axis, is called as a unique axis, which is going to have this two-fold symmetry associated with it. That means you are going to, the B axis is basically the axis of the two-fold symmetry. So whenever you look at international tables of crystallography, whenever you are talking about space groups which have this two-fold symmetry only associated with them, like monoclinic unit cells, they will usually mark A like that and a C like that. Okay, the B is usually going to be pointing outside of the page. Okay, the B is going to be pointing outside of the page, and they will mention an included angle of gamma equal to whatever, say 103.98 degrees or something like that. This sort of information will be present in what is referred to as the international tables of crystallography. Okay, we will show you some pages from that book hopefully in the next couple of lectures to see how exactly it looks. But the two-fold axis is generally chosen as the unique axis, or the axis which has the two-fold symmetry. Okay, so in addition to that, in addition to the two-fold symmetry, do you have any other symmetry elements for this Bravais lattice? Imagine, okay, let me show you the three-dimensional image so that it can be easy for you to imagine this. What can you say about if there is a mirror plane somewhere? Is there a mirror plane? Not here, definitely not with C or A as the normals. What about with B as a normal? What about with B as a normal? Do you think you have a mirror plane? You have a mirror plane, right? That is what is going to distinguish between your triclinic and your monoclinic unit cell, because you have two plane oblique lattices stacked on right on top of each other. This one is going to be your B axis, right? You have a two-fold rotation and you're going to have a mirror plane that is perpendicular to that two-fold rotation. So the space group for this thing is 2 bar m. Okay, two-fold rotation and a mirror, right? Two-fold rotation and perpendicular. If you put 2 over m means there is a two-fold rotation, and perpendicular that there is a mirror. Remember one of the rules that we just studied. It means there are mirror planes perpendicular to the B axis and 2 bar is perpendicular to it. So there is an inversion center also right in the center, and we also looked at what happens when you have 2 bar. What is 2 bar? 2 bar is two-fold rotation and an inversion center. That is also being present here, right? 2 bar is also present here, but we don't have to specify that, because if I say two-fold rotation and there is a mirror perpendicular to it, it automatically means the other one. Generally in the Hermann-Margin symbol we use this 2 over m is what is used in the Hermann-Margin symbol to talk about the symmetry.
So
yeah.
Why are we writing 2 followed by m?
2 followed by two-fold rotation is associated with the B axis. The mirror is also perpendicular to the same axis, right? If you put it in a next slot, it is associated with a different axis. It is not associated with the same axis. Okay. Now, while this might seem a little bit confusing, you will see that very quickly you will start understanding or recognizing the kind of unit cells the second you see the Hermann-Margin symbol, just like we did for the plane unit cells. Now, what happens in orthorhombic? What is orthorhombic? Orthorhombic is a rectangle, on top of that another rectangle, and everything in the side is also a rectangle, and we are talking about Bravais lattices. So there is 2 over m perpendicular to b axis, 2 over m for the a, 2 over m for the c axis. So for the 3 non-equivalent a, b and c axis, you have 2 over m, which is same as MMM. You will because now the presence of 2 mirror planes implies a twofold rotation, right? So you can also write this as MMM. There are mirrors perpendicular to all the 3 axes, or there are mirrors for which the normals are the 3 axes A, B and C axis. So this is basically the orthorhombic units. The space group for the orthorhombic units is P, 2 over m, 2 over m, 2 over m. What is the point group? What can you tell about how will you tell me what the point group is? Just remove this P. 2 over m, 2 over m, 2 over m becomes the point group. Okay. Now, what is the next Bravais lattice we can think of? Orthorhombic, then? Tetragonal. What is tetragonal now? A is equal to B. So basically you have a base is going to be a square, right? And on the sides you are going to have the corresponding rectangles, right? So in a way, at least 2 directions are similar to orthorhombic, and 1 direction is going to be similar to cubic, right? So you should be now able to write down the Hermann-Morgen symbol pretty easily. So there is going to be a 4-fold rotation. The second there is a 4-fold rotation, it makes A and the B axis equal, right? It makes A and the B axis equal, and there is no difference. So the next non-equivalent axis that you can choose is what? C. So is there a mirror perpendicular to it? Is there a 2-fold rotation about C? So there is. So 2 over m. And what is the next possible non-equivalent axis? What about the diagonals of the square? Just like how we saw for the square lattice, right? So there is going to be, this is the square, the base is the square, right? So basically this gamma is 90 degrees here, right? That makes A and B equal. So there is a 4-fold rotation about the C axis, and then the next one is basically the 2 over m, which is about the B axis, or equivalently the C axis, and then you also have these mirrors and a 2-fold rotation about them, about the 110 direction, right? So the space group for the tetragonal lattice is 4 over m, 2 over m, 2 over m, as written down over here. So now it should be very easy for us to now start writing down whatever we have studied. So first thing was triclinic. For triclinic, what did we see? We saw 1, or what did we see? We saw 1 bar. Okay. Then we saw monoclinic. What happened there? 2-fold rotation perpendicular to mirror. Then we saw orthorhombic. What did we see there? 2 by m, 2 by m, 2 by m. Then we saw this one, tetragonal, and that is 4 over m, and then we saw 2 over m and 2 over m. So in any space group, by looking at the combination and by looking at the first rotation and seeing what is there adjacent to it, you will be able to figure out what the space group or what crystal system you actually need to use in order to generate that structure. So if you see only 1 or 1 bar, then there is nothing else but triclinic. Okay. If you see 2 over m or 2 and nothing else after it, then it is monoclinic. If you see 3 mirrors, 1, 2 and 2 mirrors, okay, 1 mirror and 2, 2, 4, if you see all these combinations, it essentially means it is a orthorhombic lattice. Now if you see, the first one is 4, but after that, if it is a combination of mirror and 2, either these, then you will understand that because of the presence of four-fold rotation, you will understand that it is the tetragonal unit cell that you need to use to generate this crystal structure. Okay. Now we go to the next complicated one, which is hexagonal. Hexagon, everything is pretty much the same, okay, like what we did in the plane lattice. So obviously we are going to choose this as the unique axis, C as the unique axis, because it has the six-fold rotation. There is a six-fold rotation which is about the C axis, and there is a mirror perpendicular to it. So you have 6 over m. Okay. Now the other two axes, what were they in our? Remember, we were talking about these unit cells. What were the two axes or the mirrors that we dealt with when we talked about the hexagonal plane lattice? We talked about mirrors which had this as the normal, right? Those darkly shaded things, they were the mirrors, they were the normals to the mirrors. So basically these were the mirrors, right? In addition to that, we had mirrors which had the bisectors of these axes as the normals. So these were the mirrors themselves. The axes were mirrors themselves. For the space lattice, these two are exactly the same directions, except that now instead of having just mirrors, you also have a two-fold rotation about that axis, right? You can rotate them. For example, you can rotate the crystal about this axis and you will essentially get back the same crystal structure. And of course, there is a mirror that is perpendicular to this direction, because it is getting reflected on the other side. Is that, can you see that? So if you want, we can take a quick look at it. So this is the included angle of 120 degrees. The gamma is actually the included angle which is 120 degrees. So I said that if you rotate this, you can rotate it about this line. Are you able to see that cursor moving there? So you are able to rotate it about that line, and when you rotate it about that by 180 degrees, you will get back exactly the same crystal. And there is a mirror also that is perpendicular to it. So these atoms, when you join them, you will get a mirror. Like this, there are mirrors about all the planes for this, similar to what we had seen for the plane oblique lattice, about the same directions, with the same directions as the normals. Except that in addition to the mirror, there is also a two-fold rotation, because this is a space lattice that we are talking about. So once you see a six-fold rotation followed by 2 and 2 or m and m, or some combination like that, you will understand that it is basically a hexagonal unit cell that you have to use as soon as you see the space group. So the key thing is, when you see the space group, you should be able to identify what unit cell you can use to actually generate it on the computer, right? So these are some of the hints that you will get from the space group symbol to actually be able to generate that. The next one is cubic. Cubic becomes a little bit tricky, because there is all the three axes A, B and C have fourfold symmetry associated with them, right? The second you see 4, it could either be either be tetragonal or it could be a cubic. So now you have to try to understand how you can differentiate between space groups which start off with a 4. Okay. If it is a tetragonal, you will either see a two-fold rotation mentioned or a mirror mentioned. For the cubic, you will mostly see a 3 bar that is going to be present in the second group. Okay. In fact, this can also be M 3 bar. If you see 3 bar in the second position, it generally means cubic. It means that the symmetry is cubic. Now what does this 3 bar mean, and what direction that it refers to? The presence of the four-fold rotation is making A, B and C equal. Okay. So the next slot in the Hermann-Morgen symbol cannot be referring to either A or B or C. It has got to refer to something, none of these, something non-equivalent to A, B or C. So in cubic systems, what will happen is you have in simple cubic, if you look about through the 1 1 1 axis, okay, about the 1 1 axis, you will see that there is a 3 bar symmetry associated with that. See, is there a 3 bar? For example, consider this. So I am looking through the 1 1 1 in the 1 1 1 direction. In the 1 1 1 direction. So consider the front 3 atoms, these 3 atoms right here. So if you rotate it by 120 degrees, right, and invert it through the center, this atom rotated through 120 degrees and inverted through the center will take you to this particular atom right here, right, and you keep doing that, you will be able to understand that there is a symmetry 3 bar that is passing through the 1 1 1 direction, and there are 4 equivalent 1 1 1 directions in this simple cubic in the cubic crystal structure, right. So whether you are looking through 1 1 1 or 1 bar 1 1, all of them are essentially equivalent. So the second you see a 4-fold rotation or a mirror, and in the second slot you see a 3 bar, it will mean that the crystal structure has a cubic symmetry. Okay. The next one, the next symmetry element that is present in the cubic system is a 2 over m, which is about 1 1 0 directions. That means a 2-fold rotation, axis is the 1 1 0 direction, and perpendicular to it there is a mirror. So that's basically these, right? These are the mirrors. Those are the mirrors. There are mirrors there. Can you see it? Right. So the secret is to look for the kind of rotation that's present and what sort of symbols are present following that, and you should be able to distinguish or find out what crystal systems you can actually use to generate that crystal. And this is what you will apply for the entire 230 space group to generate the crystal structures. We still haven't gone through one more. It's called as the trigonal lattice, or the and in other words, it also generates something called as the rhombohedral lattice. This lattice is a little bit peculiar, so we will go over it in a little bit of detail. This has a 3-fold symmetry, and but otherwise it actually can use the hexagonal unit cell to be to generate this crystal structure. You can use the hexagonal unit cell. So we will see what is the difference between the hexagonal unit cell and this one. In what happens in the so in this unit cell, in the rhombohedral unit cell, what happens is the following. You have an included angle of 120 degrees. Okay, so this may be A, this may be say C, and this may be B, whatever it is. Okay, if it was just the hexagonal unit cell, you would just have this repeat with looking like a hexagon like that, right? Sorry, I didn't draw it well. So this one, that's what would be there. If you, and then you would stack this up one on top of each other to basically realize your hexagonal unit cell. Now, in the rhombohedral unit cell, you have, if you look at it from the top, you will have one more plane of atoms that's coming on top at 1/3 the height, and one more at 2/3 the height. So, there will be okay. So, it will look, if you have imagined this, then you can actually look at looking at it from top view. Okay, you have the rhombus, and then you have the first atom here that is actually present inside the unit cell, but present at a height of 1/3 from the base. Okay, and this is the corresponding rhombus that will be formed, this one right here. Okay, the second one is this atom, which is at 2/3 the height from the base. Okay, so consequently, this unit cell that you are seeing is basically like the hexagonal unit cell with an included angle of 120 degrees, except that there are two additional atoms that are going to be present at heights 1/3 and 2/3. Okay. So, you can construct the rhombohedral structure with the hexagonal unit cell by making sure that you add these additional 1/3 and 2/3 atoms as the basis to create the rhombohedral unit cell, to create the rhombohedral structure. Otherwise, you can also use this one where you have A equal to B equal to C and alpha not equal to beta not equal to gamma also to actually generate the trigonal unit cell. Convention is to use the hexagonal unit cell because it is simplest, we understand it best. So, the presence of these atoms at 1/3 and 2/3, okay, about the C axis, if you take a look at it, it destroys the 6-fold symmetry that would have been present if those two atoms were actually not there, or those two lattice points were not there. Therefore, you have only a 3/4 symmetry followed by 2/m in the other direction, any one of the other directions, to actually generate your trigonal unit cell. Okay, yeah. Which one? Previous slide? This one or? This is not responding very fast. See, if you look at it carefully, the internal atoms, the internal 1/3 and 2/3 atoms are actually going along the body diagonal of this hexagonal structure. This atom is present at height 1/3 and this one is present at height 2/3.
Those are part of the unit cell.
They are part of the unit cell. See, what are we trying? I think we have to clarify a few things. We are trying to find out the unit cell for the trigonal system. In general, the trigonal system is associated with alpha equal to beta equal to gamma, but none of them need to be equal to 90 degrees. And then you have A equal to B equal to C. So, it forms some sort of a oblique system that looks like this. This is how it should look like. Here alpha equal to beta equal to gamma and A equal to B equal to C. Okay. But when you are trying to generate this crystal structure, the convention is to not use A equal to B equal to C and arbitrary angles. It is convenient to use the hexagonal unit cell, but by placing those atoms at 1/3 and 2/3 the positions. Both this one and the other one will form the same lattice, will have the same symmetry associated with them. I don't have a good picture made to show that this one is in fact a part of that lattice, but next class I can actually bring that and show that to you to convince that this is actually lying inside the hexagonal unit cell with the 1/3 atom on and 2/3 atom on. I think you must have studied this also previously at some point of time. Okay. So, this is actually the 3 bar, the presence of the 3 bar and the 2/m should indicate to you that this is associated with the trigonal or the rhombohedral structure, for which you will appropriately use the unit cells. Yeah.
Sir, in case of the cubic, that's 4 by m, 4 by m, 4 by m.
It's not 4 by m, 4 by m, 4 by m, no. There are other symmetry elements that you need to be showing. So if it's 4 by m, there's a little bit of group theory that we may need to understand. So if you say the space group is 4 over m, 4 over m, 4 over m, okay, there are several symmetry elements that are actually present in this particular space group, okay, which I need to introduce you to before we actually talk about it in length. Okay, I will give you a simple example maybe at the end of the class. Now this group 4 by m, 4 by m, 4 by m consists of probably symmetry elements 4 over m, m, m. Now what would this mean? It would mean a crystal with tetragonal unit cell. Okay. So we are trying to represent the symmetry of, so we know the crystal structure, we know its symmetry, and we are trying to represent it using the Hermann-Morgen symbol, and then read that symbol to construct it on the computer. That is our goal. Our goal is not to, given an arbitrary crystal, classify its space group. That is not our goal. Okay, that goal is a little bit more complicated. This is a simpler goal that we have. Given the Hermann-Morgen symbol, how can we construct it on a computer? So the second you see 4 over m and some 3 bar, the second that immediately should strike to you that it is associated with the cubic unit cell. You can use a cubic unit cell to actually construct it. Yeah. Yes. Absolutely. That's why I said we are not classifying a crystal after it is given to you. I am not giving you a crystal and asking you to classify it. I am asking you to see what is appearing even after that 4 by m to recognize that it is a cubic material. Okay. Otherwise, given just a crystal and asking you to index it is probably not a very easy thing to do, or at least I don't know how to do it. Okay. But this sort of understanding is useful when you want to generate this crystal structure for performing simulations on the computer. That is the objective.